Geo Enlightenment. With us, we have Chris Crosby from Open Topography, who will be talking to us about OpenTopo's tools and capabilities. Had the opportunity to see Chris demonstrate some of OpenTopo's functionality at the National States Geographic Information Council, and have been following their work since back, I want to say, around 2016, and they do some really impressive stuff in making LiDAR data just easier to use and leveraging the San Diego supercomputer thanks to some funding from the NSF. But I stopped talking and hand things over to Chris here. And if people want to put any questions as they come up in the chat, I think Chris will try to monitor it, or Tim and I will flag things as they make sure nothing slips through.
Cool. Thanks, John and Tim, for the invitation to present. Yeah, so my name is Chris Crosby. I'm one of the leadership team members of the Open Topography project. I'm based in Colorado, but I'm actually in Washington State at the moment traveling, so I'm in this weird Airbnb space. So it's a little out of my element, and the coffee's just kicking in, so bear with me. So many of you may be familiar with Open Topography. Maybe some of you are not, and since I don't know exactly where we're at in terms of everybody's familiarity, I'm going to do kind of a high-level overview and then talk about some other things. So first, let's just do the obvious, like what is Open Topography? So Open Topography is a project that was started actually in 2009, as John said, with funding from the National Science Foundation, focused on democratizing access to high-resolution topographic data sets. And so in the very beginning, this was typically airborne LiDAR. Although, as many of you are aware, the technologies have evolved such that we can now produce really great topography from photogrammetric techniques, both from aerial imagery, but also from space-based platforms. And then there's a whole bunch of satellite data sources for topographic data, whether that's a laser altimeter like ASAT-2 or via some of the more traditional, been around for a while, topographic data sets. They're not particularly high resolution, but things like the shuttle radar topography mission, which is a 30-meter best available product. And so OpenDAR is really focused on all those types of data. And what we've been doing from day one is really focused on kind of tiered access. So co-locating the processing tools needed to derive information from data sets and make data sets easier to work with, putting those tools adjacent to the data, the raw data, so people can dynamically process through a web portal and produce these types of products. And so I'm going to show you some examples of this. So here's what I have, something like 35 to 40 minutes worth of content, I think, to talk about today. And this is sort of what I'm going to do. So I'm going to talk about an introduction to Open Topography. What is it? What can it do? Talk a little bit about USGS's 3D elevation program, LiDAR data sets, and some work we've done recently to pull those data into Open Topography and make them accessible using some cloud-based resources and other things that sit kind of behind our processing stack. I'm going to talk briefly about the state of Indiana and a kind of a case study where we have been distributing Indiana statewide LiDAR data sets through Open Topography for almost a decade now. And there's some interesting sort of patterns you can see. So I'll show you some metrics basically of how people interact with these kinds of data. And then the last thing is to talk a little bit about what happens when you have overlapping topographic data sets. And so this has been an emphasis of Open Topography now for the last several years, if not longer, is building tools to allow people to do comparisons or calculate change between topography in the web browser through the portal. And I'm going to show you an example also from Indiana, where we computed topographic difference at 1 meter resolution across the whole state based on 2 airborne LiDAR data sets. And this is really interesting to look at, and really sort of is a opportunity to think a little bit about what the future looks like as we move beyond the point where we're lucky to have 1 airborne LiDAR data set available, and we start to have perhaps multiple data sets, and the kinds of things you can see and the issues that come up. Yeah, so feel free to toss questions into the chat over here, and I'll do my best to answer them. I may table some for discussion later if they start to sound like they're longer and open-ended topics. So just to put everybody on the same page, we can produce topography from lots of different platforms or sensors, right? So And this is everything from centimeter to meter or tens of meters of spatial sort of sampling. And then there's a repeat component here where certain data sets are very easy to collect and repeat. For example, like a drone, you can fly a drone over a landscape every day if you wanted to, or small pieces of landscape. Nationwide LiDAR data sets like 3DEP are much more challenging and more expensive to collect. So kind of on the right of this image here, A, B, and C are things like LiDAR and photogrammetric techniques from kind of the near surface. So airborne LiDAR is the one that most of us are probably familiar with or most familiar with, but also terrestrial LiDAR. Terrestrial laser scanners, these are tripod mounted systems that can be used for very site-specific types of things. And then hanging a camera or some other, or maybe a LiDAR sensor on a UAS, a kite, a balloon, a camera on a pole. These are all ways to produce high resolution topographic data. And then on the left are kind of some of the classic methods like SRTM or radar from space. But also there's a vast and growing effort to kind of map the surface of the Earth using high resolution imagery, which can, as a function of collection geometry, be used to produce meter to say several meter topographic data. And then there's things like laser altimeters like ISAT too. So OpenTopography is really, we're really interested in all of these data sets, but our primary focus has been on airborne LiDAR. So mostly what I'm going to talk about today is airborne LiDAR, but just for context. So what does OpenTopography do? We're primarily an online distribution platform for point clouds, raster derivatives. So these are the digital terrain models, digital surface models, the ortho imagery that come along with data sets, as well as derivative products. And so we're not a data collection organization. We don't have capacity to go out and collect data. What we provide is a place to put the data and make the data usable for lots of different constituencies. More recently, we're now providing direct access to the full USGS 3DEP collection. So this is essentially the nearly nationwide, approaching nationwide LiDAR coverage that's available through the US Geological Survey in partnership with the states. I know Vermont has been involved in some 3DEP projects and has nearly statewide 3DEP coverage already. And I know you guys are also talking about a new statewide collection. So this is interesting and exciting, and where some of this differencing potentially becomes something to think about. We have a history of doing lots of education and training. So we've run something like 35 or 40 various short courses or trainings, both virtually and in person. These are typically focused on the academic community because that's where we get most of our funding. But we've done everything from 1-day intro to structure for motion photogrammetry types of courses to 1-week deep dives on LiDAR point cloud processing and things like that. I'm not going to talk much about that, but it is a capacity that we have and sort of a history that's helped to grow the open topography community. And because we're a set of data distribution platform, we really have focused on building partnerships with lots of organizations that represent the data collection or the data funding. And so I'll talk about the state of Indiana. I'll also briefly talk about Land Information New Zealand, which is the national mapping agency of New Zealand, who's using open topography to distribute their nationwide point cloud data set. We've also worked with various state organizations, tribal governments, some few very few commercial partners, and other federal agencies like USGS. So this is an example from Indianapolis Motor Speedway in Indiana. Just because it's kind of something interesting to look at, but these are the types of data, types of topographic data and derivatives that open topography is focused on. So sort of from complexity and size, starting on the left is the most challenging. These are the point clouds, right? So this is a interactive point cloud viewer that lives inside the open topography system that allows you to quickly clip a piece of data out and view it in 3D and change how it's displayed. So on the left right now, it's kind of watching it spin around. That's colored by elevation, where blues are low, reds are high. And then in a second, that will change to this color scheme here. And this is intensity. So because the lasers and the LiDAR scanners are near infrared lasers, they have a sort of reflectance in that near infrared. And this is an attribute of the data that you can color the data sets by. So then typically what people do, not everybody, but a lot of people do, is they take the point cloud data and they do something to it to produce a different product, a raster derivative. So this is just simple geospatial gridding. And open topography has tools to do this dynamically. We also host sort of pre-computed products that typically come along with the data set. So these are the DTMs, DSMs, intensity grids, sometimes canopy height models, other sorts of derivatives from the LiDAR. And then downstream of that, we provide tools to do things like generate vectors, so the contour lines, for example, or to produce raster derivatives, such as I want a map of aspect or slope or surface roughness. We have tools to do all of this inside of Open Topography kind of dynamically. And I'll show you sort of an example of how this works in a second. As I said in the very beginning, Open Topography was founded in 2009. So we've been doing this sort of in a production capacity since that time. So for now, over a dozen years. The project is a collaboration between the San Diego Supercomputer Center, UNAVCO, which is a non-profit supported primarily by the National Science Foundation based in Boulder, Colorado. This is who I work for. And then Arizona State University. And all of our funding, essentially, with some exceptions, has come from the National Science Foundation. So, and specifically the geoscience division of the National Science Foundation. So really, we exist from National Science Foundation's perspective to support academic research and education. That's the primary emphasis. And that's like when we write proposals every 4 or 5 years to request new funding, the context is really that scientific impact, that facilitation of research. In practice, though, lots of other people use Open Topography for lots of other things that are beyond that. And so it's sort of roughly a third of our user community identifies as an academic of some form, a student, a grad student, a postdoc, faculty, et cetera. And as John said at the very beginning, one of the things that we've always done from day one is this emphasis on co-location of data and processing, and we heavily leverage resources available at the San Diego Supercomputer Center. So in the lower right is no longer active supercomputer. It's been just recently replaced, but we actually have allocations on some of these machines directly from the computing center to run processing tools. And we also heavily leverage kind of commercial cloud-like systems at the supercomputer center for things like data storage. So this has been one of the great successes of Open Topography, is this close collaboration between geospatial professionals, geoscience experts, and the computing folks. And so this image in the upper left is the Open Topography team. As it is today, everybody has multiple jobs beyond Open Topography, but these are the folks that sort of make Open Topo happen. So Open Topo is really all about the data. So this is, and we'll dive into some of these topics a little bit more, but it's good to lead with this. So this is just a screen capture from the Open Topo Find data map as of yesterday. We're a US nationally funded program, so we're pretty US centric, especially with regard to LiDAR data sets. We do have this collaboration with New Zealand, which I'll talk more about in a second. They're currently available through Open Topography, something like 47 trillion LiDAR points from either laser scanners or photogrammetric processing workflows. The vast majority of that is the USGS's 3DEP program, which are the green polygons on this map. The red polygons on the map are data sets that come from other partners that Open Topography stores kind of on premise, as opposed to 3DEP data, which we retrieve from a cloud resource, which I'll talk more about that in a few minutes as well. And then, as I said, beyond the kind of LiDAR data sets, we also are really focused on just topography at the global scale. So we currently have about 12 different global or sort of regional topographic data sets. So this is everything from SRTM, the NASA DEM, ALOS World 3D, the new Copernicus DEMs, as well as data sets like the USGS's 3DEP, which many of us used to know as the National Elevation Dataset, NED, which is available at 1 meter, 10 meters, and 30 meters. And so all of those data sets are also available through Open Topography. So this is a growing catalog of data. We're about to ingest actually and offer all of NOAA's LiDAR data sets through a similar process that we do with 3DEP. That's something we're currently beta testing, will become live soon. So that'll be very coastally focused. But these are the data sets you might find if you go to the NOAA's Digital Coasts repository. And those will become available in Open Topography shortly. So talking a little bit more about services, since that's really the magic of Open Topography, is that we don't just deliver the sort of raw data. So you're not downloading tiles of point cloud data in LAS or LAZ format. You can get that from us, but that's sort of not what we typically see users doing. We provide these set of services that allow you to kind kind of quickly, easily do an area of interest clip of a data set, produce a visualization, produce a derivative like a DEM. The vast majority of users, I think, in the geospatial space still to this day, even though point cloud data has become much more ubiquitous and better supported in software, primarily work in kind of raster or vector spaces with topographic data. The raw point cloud data typically is used for modeling or analysis. Increasingly, people start with point clouds and want access to raw point clouds, but those are the most challenging of the data products to work with. And so, there's this like sort of this figure shows arrows going in opposite directions of accessibility and ease of use versus data volumes and computational demands. Point clouds at one side and something really simple like a Google Earth KMZ image at the other end. And we try to serve users at the full range of that spectrum. So if you want to download data in bulk in point cloud format, have at it. We have that capacity. But if you want to be able to click a few buttons in the web portal and download a hillshade image, you can stick on a clipboard and take it out in the field and map on it. You can do that through Open Topography as well. And then appreciating that not everybody wants to interact with a portal, especially in this age of kind of moves towards cloud native types of data. We do have a growing set of services. So we have the portals for people who want them, but we also have some APIs, kind of simple RESTful APIs to access data and metadata. We do bulk download services. So we've moved most of our holdings into cloud optimized geotiffs. So you can interact directly with the data sets in the cloud without these kind of download to local types of mechanisms. And this is definitely a growth area, an area we're continuing to develop capacity. So thinking about services broken down a little bit more, here's the sort of set of services. So we've got this big bucket of data. That's actually lots of buckets of data from different places. Then we have tools to do basic data selection. So that's sort of spatial subsetting or attribute-based filtering for both point cloud and raster data sets. And then there's a whole suite of tools for kind of deriving products from that raw data. So that's one might be making a 3D visualization of the data set, kind of like the Indianapolis Motor Speedway example I showed you, but also creating simple raster derivatives using a couple of different gridding types of algorithms. We have tools to make a canopy height model, topographic hillshade, slope, aspect, roughness, generate contour lines. And all this is done dynamically and on the fly. So we're not pre-computing these products, we're actually computing them when they're asked for. As I mentioned at the very beginning, we're really interested in differencing and multi-temporal change. And so we have tools now for both computing the difference in data sets in the vertical. So this is like Z difference, so essentially raster subtraction. And then some more sort of application-specific tools for doing full 3D point cloud displacements, which I won't talk about here, but these are really relevant for things like earthquakes and other types of, sort of geophysical events where the landscape is moving in 3 dimensions, not just like an example of like an erosional process, which would be a vertical change. And then we also have tools for hydrology. So we run TauDM on an HPC allocation at the San Diego Supercomputer Center. This is sort of like ArcHydro for those of you who dabbled in ARC space. And that's that's available as well. And I won't talk much about that today. So quickly, what does this look like in practice? If you come to Open Topography, I'm not going to do a live demo because that tends to take a little bit longer, but like most geospatial portals, we have a fine data map where you can make a selection for an area of interest. And this is coastal California in this example. So again, red data sets are these ones that are collected for sort of National Science Foundation research applications or other special events. So like, for example, these red long lines are the faults of the San Andreas fault system and Eastern California shear zone. The green are the USGS 3DEP data sets for California. After you make that selection, a window pops up. It shows you the available data sets are organized by tab. So these are data sets that are either available through the Open Topography core catalog via the USGS, global data sets. So this is the SRTMs of the world. And then you can choose what type of data product you want. Do you want the point cloud? Do you want the raster? And then you'll notice that some of these have a little button that says differencing. So these are data sets that can be compared to another overlapping data set through the differencing tools. Each data set has a landing page, and we've spent a lot of time and effort trying to make sure that we do data attribution and credit properly, because again, we're not the authoritative source for these data sets. We're kind of the middle person between the user and the collector or the funder. So data sets have landing pages with metadata, logos, and information. Every data set gets a digital object identifier, which is something you'd use if you're citing a data set, say in an academic publication. And then data access links, so links to download data via a map interface or a bulk kind of cloud download. Essentially, OpenTopography is just you're parameterizing a processing workflow. So you make a spatial selection, and then you choose what subset of the data set you want. Say, for example, for a LiDAR point cloud data set, you might say, I would want just the ground points for this data set. And so we'll do that selection on the fly for you. And then formats and outputs. So I want data in LAS format. I want data in LAZ format. I want data as an ASCII point cloud, which I don't recommend, but people still do occasionally ask for. And then we have tools for making digital elevation models dynamically from those points. So this is using either a TIN or a local gridding approach. You can define your resolution of your product, some other sort of knobs and buttons to turn, and then your output format. So like I want this as a geotiff, or I want it as an IMG grid. And then from that DEM, if you can make visualizations, so you can do hillshade, color relief, color hillshade, slope, aspect, roughness. You can generate a point cloud visualization. We can make you contour lines. And then if you go down this page a little further, you see some of the tools for the hydrologic routing. When you hit submit, this job goes out and it runs in real time on compute infrastructure at the San Diego Supercomputer Center primarily. And within typically, we say the time it takes to walk down the hall and refill your coffee, a job comes back with the products you asked for. So this is an example landing page. You also get an email at the top of the page. You have links to download the sort of GIS products, the raster products, the point clouds, contour line, geodatabase, whatever it is, so that you can put that into your software package and do your continuing analysis. And then we also produce these kind of browse type products. So this is an example from Salt Lake. This is the Capitol building for the state of Utah. And so these are the raster products that were quickly produced. You can see in this job, I think it says 20 some odd seconds, so 50 seconds up there. So this is a relatively small job. There's only 5.5 million-ish LiDAR points retrieved and processed in tens of seconds. And that's pretty typical for open topography. Obviously, the bigger the job, the longer things run, but it's pretty rare for jobs to go more than tens of minutes for really large jobs. And so this is really nice because it encourages exploration of data. So for example, I'm curious what this data set looks like if I regrid it at 2 meters, or if I change the contour line interval or something. We can do all that processing pretty dynamically and pretty quickly. And you don't have to do any of it on your own. So you can have other things going on locally while you're letting us do the work. This is this interactive point cloud viewer that we provide inside of Open Topography. So this is a point cloud data set that's been clipped out of this Utah data set. This is colored in this case by red, green, blue values. So this is RGB assigned to each pixel coming from optical imagery that was collected synchronously with the LiDAR collection. And so this is some data sets have this RGB as an attribute, but not all of them do. This interface is really cool. Makes it really easy to explore data sets. You can cut profiles through data. You can change how the data are displayed. And it's all, again, running in the web browser. So this is not a viewer you download. So that's kind of like what the OpenTopo web portal experience looks like. I encourage you to go opentopography.org and click on the data button at the top and start poking around. But that's sort of the basic end-to-end process. Quickly talking about other pathways. So we currently have an API that allows you to quickly grab these kind of global data sets. So the SRTMs, Copernicus, et cetera, global data sets at 30 and 90 meters. This is a RESTful, simple RESTful call. So it's really easy to embed into a processing script. A lot of pieces of software, open source software, have embedded this API inside of them. So like Blender has a get topography function that's calling open topography to pull that data. And there's lots of other tools out there in the open source world that are built on top of this. And then we also are providing programmatic access to data through these cloud optimized geotiffs for rasters. And so this is an example from our GitHub repo where we have a Jupyter notebook that sort of teaches you how to use cogs in combination with open source software like GDAL to do kind of processing on data remotely. And so this is one of several resources that live inside of our GitHub, but this one's focused on COGS. So moving on a little bit here to talk a little bit more about USGS's 3DEP project, since I know this is something that's quite of interest to states in particular, since a lot of you are working through the 3DEP program to get data. So one of the interesting things about 3DEP is this is obviously the grill in the room for at least the United States in terms of LiDAR collection. This is the largest investment in data collection. It's the most ambitious in terms of spatial coverage. And it's a consistent data set because there is the USGS's 3DEP LiDAR spec. So these data sets are at least mostly are consistent. When you dig into them, they're not, but functionally they're relatively consistent data. And so USGS has their standard national map interfaces to download these data by tile. But a few years ago, one of the things that they did in partnership with Amazon Web Services is they now are publishing these data into Amazon into what are called a public dataset bucket. So this is just a big old S3 repo that has these data in them. If you want to get them in LAZ format, the kind of standard point cloud exchange format, you have to pay the egress costs associated with them. But they're also in there as this format called endpoint point tiles, in which Amazon is covering the costs of data egress. And so we are actually built a few years ago a whole system on top of this. And so where a user can dynamically every week sync with the AWS bucket, integrate new data sets, sort of scrape as much metadata as we can, and then allow a user to use Open Topography's processing tools on top of that big repo, whatever it is, 45 trillion LiDAR points inside of the 3DEP program. So a few new data sets per week are added to this because USGS publishes a new data set, a couple of data sets. It's I think the goal is complete coverage in the next year or two. So there's definitely more coming. But this is what it looks like. This is basically the same map I showed at the very beginning. So it's 45 trillion LiDAR returns over 7 million square kilometers currently in the USGS 3DEP program. And then the other thing that's available through Open Topography are the 3DEP raster derivatives. So for every point cloud data set, USGS goes through a process of QA/QC and then converts that data into a 1 meter digital terrain model, so the bare earth product, and then uses that same data set to rebuild the 10 and 30 meter, like historically what we would have called the national elevation data set products. And these are all accessible through Open Topography as simple clip and ship types of operations. In a cartoony sense, this is kind of interesting because if you use this through Open Topography, you don't really maybe appreciate this, but when you make a request, we actually go from the San Diego Supercomputer Center over to US West Oregon regions, Amazon data center, grab the data subset, bring it back to San Diego, and then process it through our standard set of tools. And so this is kind of a cool opportunity for us to leverage this move towards cloud native data and large organizations publishing their data into these resources without us having to hold a copy of the data locally, because that's relatively expensive. So in this case, Amazon's covering that piece, and we're providing the services on top of it. It is worth noting right now that USGS 3DEP and Open Topography is currently limited to academic users. So if you have a .edu email address, you can log into Open Topography and click a button and activate this capability. We haven't exposed it more broadly. So this is the only thing in Open Topography that's sort of access limited at the moment is 3DEP. And that's because our experience is that tons of people would be interested in these data sets. And we would expect that the utilization of them to be far larger than we have the resources to support. So, on-demand compute is something that takes resources to support. And the National Science Foundation has been quite generous, but is not interested necessarily in helping to serve this data more broadly because they're interested in science and education primarily, not in sort of geospatial data infrastructures, that they feel like that's something the USGS or the states or other organizations to be focused on. So this is something we're trying to navigate right now, is how to try to unlock 3DEP for everybody through Open Topography. And there'll hopefully be some updates on that this coming year at least. So quickly, moving now sort of into other other examples of people using Open Topography to make their data available. So as I said, we're the partner with Land Information New Zealand to host the data they're collecting through their national LiDAR program. So right now there's 56 LiDAR point cloud data set, polygons covering about 79,000 square kilometers in New Zealand. That's the map on the left. these data sets come in. We get about one per month from New Zealand. And they're on a mission to complete national coverage in the next couple of years. It's obviously a much smaller country than the United States. So it's a program that looks a lot like 3DEP, but is obviously a little bit easier to achieve coverage. But this has been a really fruitful collaboration, and there's a lot of really cool and interesting geology and geography in New Zealand. So it's a really fun place to go poke around if you're interested in that. The other kind of case study, or the bigger case study, was to look at the state of Indiana. So in 2012 or so, state of Indiana was in the middle of a statewide LiDAR collection, and they had all this point cloud data they didn't know what to do with. And they had found open topography. This is still pretty early days of open topo. And they approached us and said, we don't have a great way to distribute these data. Would you guys be interested in hosting them? And so we, for a relatively low fee, we took the data set and put it into open topography. And so we've been running the Indiana statewide LiDAR data in open topo for the last decade. And so it's a kind of interesting data set to look a little bit about how people use these data and what their experience has been. So one of the big things is this is the most popular LiDAR data set in open topography, probably not surprisingly. It gets used by a very diverse set of communities. So governments, commercial sector, surveying, engineering. We see a lot of agriculture and irrigation utilizations, irrigation planning, because it is Indiana, energy, lots of other uses. And so this is downtown Indianapolis in this little spinning movie of in the viewer. So looking at metrics, one of the things open topography is pretty, we're well instrumented in the sense that we keep track of, we log everything. So we have lots and lots and lots of information about utilization of data sets. So on the left is this plot of Indiana data use by month going, this goes through the end of 2021. So we basically need to update this plot for this year, but shows you kind of the temporal use of these data. And one of the interesting things about this is that you see no die-off. So these geospatial data sets are valuable for use long after they've actually been collected. And actually there's a newer statewide Indiana data set that's in 3DEP. And yet we don't see a decline in use of the older data. People still find these data really useful. The other thing that we keep track of is spatial selections. So this is a heat map of utilization for the state of Indiana. Like, where are people downloading data? And we do this by just taking people's area of interest selections and stacking them and just building heat maps. And so this is kind of a fun thing to explore. And actually every data set in open topography, if you go in the upper right of the map that you would make a selection on, there's a little box that says show heat map. And it turns this on. So you can fly around and look. You do this for Vermont and see where people have been accessing data in Vermont. Obviously, this tends to go with population. So Indianapolis, Lafayette, places like Chicago, places like that tend to have pretty heavy utilization, but not always. And so this is something that is interesting to think about. It's also potentially informs how you manage data, hot data versus cold data. It also potentially informs where you might target future data recollection if you were in charge of planning the next collection. Where would people be most interested in, where would your largest return on investment be? As I said, we see lots and lots of different use cases of these data, lots of companies and organizations that you recognize, and then lots of small mom and pop type shops. There's a podcast that Phil Worrell, who was the coordinator for the Indiana Geographic Information Council, was on this State Scoop GIS Address podcast that talks about kind of GIS topics for the states, and they were talking about elevation data distribution. And they've had a good experience with open topography because they found that this adding this layer of services that make data easy to use really unlocks the data for lots of constituencies, and that's pretty powerful if you're thinking about return on investment, because these are not inexpensive data sets to collect, right? We see this across open topography more broadly, that by putting easy tools that make data easy to use, people go out and do all kinds of really interesting and weird things with them. So these are just some quotes from, we have this like form where you can request power user, basically enhanced processing limits. And we ask people what they're why they need to have a higher processing limit. So this is just a very, very, very small subset, but sure shows the diversity of things, everything from hazards to science and research to recreational applications, hobby applications. We see a lot of use for these data sets in the kind of growing virtual world space. So this is people pulling data sets to build video games and like virtual environments. 3D printing is a massive use of open topography, both recreationally. So this is somebody, the lower pictures are from a thing I stumbled upon where somebody actually has like an Etsy type of store where they 3D print their favorite rock climbing locations and then pitch them to other rock climbers. And they're actually pulling the data from open topography to do that. So what this has been, I think, one of the great most powerful things about open topography is the demonstration that, it's great to have open data, but actually if you really want to make that data equitable for people to use and take full advantage of, adding that layer of tools that make it easier for people to discover, do more than just discover the data, but also to derive products that they want in a relatively easy way, really leads to creative applications and data reuse. So that's a little bit of a sales pitch, I guess, but I think it is an interesting lesson for anybody who manages geospatial data. So moving on, I was going to finish with a few slides about this topic of topographic differencing, because I think it's an interesting one, because we're entering an age when we actually are potentially have the opportunity to compare high resolution data sets over relatively large swaths of landscape. And that's sort of what happens when you do this. So what you see. So we have a relatively new paper that was published earlier this year called Statewide USGS 3-Depth LiDAR Topographic Differencing Applied to Indiana. It's in remote sensing. It's an open access paper, so that digital object identifier will take you to the place you can download the PDF. But what we basically did in synthesis was we went and we took all the LiDAR data across Indiana from the 2011 to 2013 collection and the collection that just finished more recently in 2021. And basically computed, we took the point clouds, we converted them to consistent raster 1 meter resolution DEMs, DTMs, and then we calculated the difference between them. And there's a browsable map, which allows you to go look at this. And so you might ask, why Indiana? It's a state that has two statewide LiDAR data sets, which is interesting in and of itself. We had a pre-existing relationship with Indiana through our partnership for the 2011 to 2013 data set. And we were really interested in just like, what does it look like to do this? What does it take to do this from a technical implementation perspective? And then what do you see? So quickly, I think most people on this call are GIS folks, and so this should be maybe obvious, but just to talk through it very quickly, the way that this works is what we do is we take what we call the compare data set, which is typically the earlier one, and we take the reference, which would be the post data set. And typically they're different point densities because LiDAR data sets tend to be increasing in point density just as a function of laser scanner technology. And then we grid them to the exact same grid. So there's no like half pixel offsets or anything. We also in this process address coordinate systems, so vertical datums and other coordinate systems that would lead to erroneous change. And then, quite simply, you just do some simple raster math and you subtract. And I'm going to show you a bunch of these blue to red maps. So just quickly, the red indicates the landscape going down. So that's erosion or removal of material, and up is blue. So wrap your head around that because we're going to see a whole bunch of this here in a second. I won't go through the details of how this was done, but we had this kind of big scripted process running on a relatively big machine, pulling data from the cloud, producing products. We also computed canopy height models, and then we published the whole thing into a web browsable map that's online. So what are the challenges with doing this? The final products for this exercise, so 1 meter change of DTM, DSM, canopy height, is something like 4 terabytes. We did this on a fast machine, a big machine. So to do this we calculated to do this like locally on your laptop or a decent GIS workstation might take you something like a year. And there was a fair amount of kind of wrangling to get this optimized, especially because we were relying on remote data sources and so making sure things completed and didn't time out and all kinds of things like that. And then what does this look like? So here's Indiana zoomed out. So left is the digital terrain model difference. So this is the bare earth to bare earth. And on the right is the digital surface model. And so when you're zoomed way out looking at the state, you see a bunch of stuff. And the signals, largely in terms of what are the things that are changing kind of on the decadal scale across the state of Indiana, are, if you look at the DSM on the right, fluvial and riparian environments. So rivers, meandering, depositing point bars, eroding cut banks. Vegetation change or apparent vegetation change. So this is seasonality. So if you fly LiDAR leaf on and then your next collection is leaf off, you're going to see change in vegetation. Or if you have a collect that takes more than a season, you obviously see that as well. You see a lot of quarry and mining activity, and kind of these extractive types of processes, digging and moving materials. And then most dominantly in the DTM, you see alignment errors in the LiDAR data. So this is like one of my take-home messages, is that the quality of your topographic change is only as good as your source data. And so you can see in that left DTM panel, red and blue stripes going north-south and red and blue stripes going east-west. And those are the artifacts of the flight direction. So either the aircraft's flying north-south or the aircraft's flying east-west. And and this is common in LiDAR data, is you get kinematic positioning errors associated primarily with where the airplane is in space that propagate into the accuracy of the data. And so if you have a, say, decimeter or 15 centimeter positional error associated with your data set, and you difference it with another data set, if that one also has a decimeter or greater error, then you potentially could have a 25 centimeter or more aggregate change, apparent change. These tend to have very long wavelengths because they have to do with positioning of the aircraft as it's a moving platform through the air. So it has a longer wavelength that goes with GPS accuracy and baseline length and a whole bunch of other factors. Some of this can be processed out, but it's very manually intensive to do so. And we did not do that in this exercise kind of deliberately because we wanted to illustrate some of these things. This is getting better. The commercial industry has gotten a lot better at LiDAR overall. And so I think it's safe to say that most of these errors are in the old data set, the 2011 to 2013 statewide collect, and that the newer data would be better, although we haven't fully tackled that. So just a couple of quick examples. So here, I'm going to go through quickly a couple of panels here and then we'll wrap up. So just showing you the kinds of signals you see. So in the left panel is the pre-event topography, or being 2011, 2013. And then the center panel is the more recent statewide LiDAR for Indiana. And then the panel on the right is the difference. Again, with red being down and blue being up. So first one's a fluvial meander example. You can see this like meandering channel here, quarry erosion in the lower panel. In the upper panel, one thing I'll point out is that you see very distinctly a vertical red stripe and then on the right side a vertical blue stripe, and that's kinematic positioning error in the LiDAR data. That's not a real signal. And so these are the things that start to come out when you look at the data. Here's another one. This is construction, like kind of suburban housing development around Indianapolis. So blue are new buildings coming up, new houses. The lower one is a highway interchange where they reconstructed the ramps and reconfigured it and built new curly exit ramps. Another interesting thing from a hazard perspective, we see sinkholes. So here's a bunch of places where, interestingly, the sinkholes are blue, right? So they're coming up. What's that? So they're probably full of water or something. So it's seasonal. In some cases, they've gone down, but there are quite a few that have, or they've been filled in by some other process like humans. And so that's another interesting one that we were surprised to see. Here's construction at the Indiana University football stadium, where they built new bleachers, it looks like, at the south end of the stadium. And so this is a really interesting exercise that was done. We did as a very brute force attempt to demonstrate what this looks like. But if you look forward and you dig into the 3-up catalog, as well as some of the other large public repositories of data sort of at the state level, we think there's about a third of the lower 48 that's currently covered by repeat data. And so you could do this exercise over about a third of the United States if you were so inclined. it's a really interesting opportunity to characterize this change in anthropogenic and natural landscapes at sort of whatever the bracketing time period is for the LiDAR data sets. And this is the great challenge, is that LiDAR is pretty infrequent compared to, say, synthetic aperture radar or optical imagery, where you might have a much more frequent repeat time. But for things like biomass change, some kinds of hazards, it's a pretty interesting tool. But the challenges here are that to analyze this data set took a lot of time. We've learned a lot, so I think we've gotten better. That we could do this more efficiently in the future. But actually, the next problem is like making sense of those change maps. So, you know, every pixel has a signal of some, and trying to pull them apart and figure out, is this erosion? Is this home development? Is this error? Is something really complicated. And so we're starting to do some machine learning on these change maps to see if we can figure out how to do this programmatically, so you could walk the whole state and attempt to bin the data sets into class of change. So I think that's basically it. This is my last slide. These are just sort of some maybe take-home points that we've learned about open topography. And I think I've said basically all of these, but just that, you know, making data easy to use leads to greater return on investment. Open topography, we spent a lot of time on sort of service durability, availability, and customer support. Analytics on how people use your data are really interesting and help potentially justify your existence or funding for new data. And then I think the final take home, which is this conversation about change, about the change, is that, you know, treating LiDAR truly as big data, that these national scale large data sets present really interesting opportunities, but also require really modern approaches to how you handle them and sort of organize them such so that you can optimize them. So thanks again for the time and allowing me to talk about OpenTopo. We're always interested in hearing from users. So if you have questions, shoot me an email. I'm easy to find, or email info@OpenTopography. We'll get back to you, we promise. And then also we have all the standard social media channels. So thank you very much.
Thank you, Chris. That was great. And I think some very relevant and timely material for us to think of as we move towards getting a statewide collection. That would mean that Vermont would be covered in its entirety with 2 complete data sets, and the change or the differencing stuff is super interesting. I guess I'm curious what with regards to either tools or research in the pipeline, where do you see the focus of open topography, and what do you think we can expect in the coming couple of years?
Yeah, that's a good question. So we're working on more stuff related to change, largely related to, right now, the big issue, especially with the 3-dep data sets, is actually inconsistency in things like vertical datums. So surprisingly, the whole 3-dep data set is not all on the same vert. And so if you want to do intercomparison of 3-dep with other 3-dep data sets, or with 3-dep with things from outside 3-dep, say like open topography hosted data, you got to solve that problem. And so we're working on, we have a system in beta we've been working on, is basically just trying to do some of that dynamic, like basically a change geoid models on the fly kind of thing. So you could say, okay, we're gonna make these data sets line up dynamically, and then we're gonna process the change between them. That's one thing that's going on. Another thing is, I mentioned that we're gonna pull the NOAA Digital Coasts LiDAR catalog into open topography, and that's really very coastally centric because it's NOAA. But it's really interesting because there, in some places like Southern California, there's been a flight every year along the Southern California coastline since like the early 2000s. And so it's really actually an interesting catalog of data, and some of the highest frequency LiDAR data in dynamic landscapes. That should be an interesting place for sort of change and other applications. And then still a lot of more API access. So we're working on putting APIs in front of things. So right now our API for the global data sets gets pounded. Like 3.5 million, jobs run against that API or something, because it's out there. It's so easy to use, but right now it doesn't expose point cloud data and high resolution raster data. And so that's something we're working on, is like an API, a simple REST API that sits in front of, say, the USGS's 1 meter 3-dep data set. So you can just clip that out through a scripted process. So I think those are a couple of things that I'd say are coming soon. Oh, and actually, I guess the fourth one is, which is maybe interesting for Vermont, is as a pretty forested state, is more forestry metrics. So more tools. Right now we calculate canopy height. It's the only thing we do, but we've been looking at, we have a collaboration right now with some wildfire oriented research project, with an wildfire oriented research project at the Supercomputer Center, where they're trying to derive full like fuel models. So like basically integrating vegetation biomass into a wildfire propagation model. And so to do that, you have to really handle the point cloud and process a lot of the derivatives to really, height above ground vegetation and other things. And then basically like a grid metric based approach to forestry, kind of LiDAR derived forestry products. So that's also something that we're starting to dig into. Because OpenTopo is very solid earth centric. We're really focused on like, bare earth topography. It has been our history because of this geoscience emphasis.
Tim.
Chris, thanks for that. Can you say a bit more about, you mentioned briefly, potential noise removal in the differencing models?
Yeah.
What considerations come into play for noise removal such that the interpretation of the differencing products isn't misinterpreted or misused?
Yeah, for sure. This is tricky. So, if you come, let me just get back to this slide quickly. Yeah, this one. Yeah, so there's the positional error, which is it's typically is sort of these long wavelength GPS errors, drift errors, like, where the kinematic position of the aircraft changes by a few centimeters as the plane flies along its trajectory. There are some tools out there that you can use. The strip align tool by BaseMap is something that's pretty cool. It's a very specialized tool. It's meant to help you back some of this information out. It works best if you have the SBET files, which are the aircraft trajectory files available. And so for a lot of data sets, those aren't available. You can also do this brute force by like calculating difference and sort of chunking the data and doing like a cloud to cloud alignment along the flight line to kind of stamp down the errors there. It's very labor intensive. I have a colleague who's been doing a landslide inventory for the state of Minnesota based on repeat LiDAR, and he has done this, but it's taken him a long time, and he hasn't done it for the whole state. He's just done it for the kind of cliff bluffs where they see landslides. I think he has a paper that's like in the works on this. That's one way to do it. The other thing that we also see in this that I didn't really talk that much about is classification consistency, right? So like how you run your classification algorithm to differentiate ground points from vegetation points or building points for vegetation or whatever. That classification routine needs to be consistent across this. So if your data set, the first data set was collected by one vendor who did it one way, and the second data set was collected by another vendor who did it a different way, that's going to lead to potentially difference. If in one data set, a point that is ground is classed as veg or something. And then also consistency within a data set. So some of these big LiDAR data sets, I think, do get offshored for processing I have definitely seen LiDAR data sets where like one tile, you look at what the tile did and then you cross over to the next tile and they actually have different classifications across the tile boundary because the analyst who was sitting in front of the computer running the processing workflow was using a slightly different set of parameterization than the guy next to him, that analyst. And so that consistency also does appear. But in this data set in particular, for Indiana, it's these longer wavelength swath misalignments that are really most prominent, especially when zoomed way out, looking at the whole state. But there is this browsable map. If you just go to opentopography.org/Indiana, basically we have it just all loaded in GeoServer, so you can kind of cruise around and look at it yourself. It's really interesting. Other questions?
Great. Looks like Kay has her hand up.
Hello, can you hear me?
Yes.
I was wondering on your differencing, is the ability to go back in time available on the differencing, and is the data going to be saved historically?
Yeah, so the difference is really just it's a one time stamp, right? It's basically the difference between a data set collected in the early 2010s and a data set collected around 2020, 2021. That's But actually, because it took them over 3 years to fly the first data set, you know, region to region, the time differential is a little bit plus or minus. Certainly, we think that these legacy data sets in general, like the pre-best available data, are super interesting, and we, for our perspective, definitely want to keep those data sets around because they represent a pre-event baseline for any future thing that might happen. So we have them, and I think USGS is working on finishing the nationwide initial coverage, and then the next question is going to be repeats. And so who's going to come forward and want to fly a second collect? It sounds like Vermont is talking about doing this. For sure, maybe USGS will start doing targeted repeat collects, over populous areas where things are changing, or over dynamic landscapes where things are changing, depending on the motivations. One of the stories I like to tell is that one of the oldest data sets in open topography was collected by this NSF-funded group called NCALM in like 2001 or something like that. It's a really old and probably pretty bad data set because it was the very early days of wide-scale airborne LiDAR collection. But a few years ago, there was an earthquake in Napa, California. And that earthquake happened directly inside the footprint of that very, very, very first airborne LiDAR data set that NCALM collected. And under normal circumstances, you'd be like, oh, well, that Napa data set's kind of junk. Like, it's not worth looking at. There's better data there. But suddenly that data set was the pre-earthquake